Hello students, welcome back to Engineering Mechanics Dynamics. This is our second session. In previous session we studied rectilinear kinematics. In this lecture we're going to solve some problem on rectilinear kinematics. So today's learning objective is to be able to discuss basic steps for solving problems. So if there is so solving problems is sometimes very easy for some of us, but sometimes it is hard for some of us to figure out how or where do we start and how do we solve the problems. And it can always can be made simplified if we follow certain steps. So we're going to talk about that, and then we're going to solve some rectilinear kinematics problem. So let's move to the next slide. So why do we solve problems? Solving problem is an effective way of learning. So if we solve problem, it will be effective, very effective for us to be able to understand and apply dynamics. Problem solving, like I said, can be much simplified by breaking down the whole problem into subsequent steps. I have made some basic steps that I'll follow in my lectures. If we follow these steps, the problem will be much simpler, but you are always welcome to develop your own solution steps, or you can add more details into those basic steps that I have listed here, the way it is better for you. So the first step for solving a problem is to find knowns and unknowns. To do that, we should read the problem very carefully and identify from the given data what is known, what are the data given, and what is unknown, what the problem is asking for. We also have to look for any special consideration or assumption is stated in the problem. So once we identified the knowns and unknowns, then our next step would be drawing any necessary diagram. Diagram also helps us to understand the problem and solve the problem easily, and it also helps for the reader to read the solution easily. So we have to draw all the necessary diagram and label properly. Then we have to make a plan for the solution, how step by step we're gonna solve the problem by correlating the knowns and unknowns to the theory we have learned in previous classes. So if we can connect the knowns given and the unknowns, what is asked for, to the theory, the theoretical equation that we have, then we can use those equations to solve the problem. And just a cross check before we go to the solution, we have to check if the units are consistent. Sometimes in a given problem, the units of the data is not consistent, not in the same standard unit. Then we have to convert them into same standard units. Once we're done with this, then we can move to the solution. So we have to find solution by solving the relative equation that we have identified, and while we do that, we need to show all the necessary steps for solving problem. So do not skip a step while you're solving a problem, solving an equation, and it is necessary to get full credit. So full credit in exam and homework. So do not skip any step in your homework or in your exam, and this is also helpful to get partial credit. For example, if you ran out of time and you do not get the final answer, you can still get some points, partial credit, if you show the necessary steps. Or if your final answer is wrong or due to a typo or miscalculation, you can still get some point if you do show necessary step and do not skip steps of solving equations. Finally, once you arrive at a solution, check for units. So unit of your answer, does it make sense? And also physical realism of the solution. So the numerical result you got, does it make any sense? And sometimes in some problem you have to make decision based on your results. So also you have to check, does the decision I'm proposing whether it is make any sense or not. So after those cross checks, once you're ready to finalize your answer, so you can box out your answer, and it's easy for us to find out which one is your answer. So always box out your final answer. Alright, so let's move ahead and solve some problem. Today we're going to solve 3 problems. The first example problem, it says a particle is fired vertically upward at 50 meter per second. So this is a given thing, so let's find out the knowns. So it's the initial velocity, so u 50 meter per second, and the particle experience a deceleration, which is opposite of acceleration, that is defined as a equals to 100 over velocity, and unit is meter per second is square. So one thing to notice is that a is not constant, is a function of velocity. So it's a function of velocity and it's not constant. So these two things are given. So what are the unknowns? I always write the knowns and unknowns on the very right side, so I can start find solution here. Okay, so what are the unknowns? It says determine the maximum height. So S max is unknown, which is the maximum height, and reached by the particle, and required time to reach the maximum height is t. So these are the unknowns. So once we identify the unknowns, now we can plan for a solution. We can also draw a diagram. So its particle is moving upward. The problem is asking what's the maximum the particle can go with the initial velocity of 50. So at that position, at maximum, my final velocity would be 0, and it also asks for the time. So time to reach the final velocity and the distance S max. Here, so we need this distance. S max. Okay. Let me write it down. S max. That's what we're looking for. Okay. Now, at the beginning of the solution, we need to think, how can I connect my knowns with unknowns? So I have acceleration given, and I'm looking for time and displacement. So one way to start is that I know the definition of acceleration is dv over dt, and I know that a is given as a function of velocity, so I know I have to start with this one. I can start with this one. So I can simplify this as a dt, because I'm looking for time, so dt on this side and dv over a. Now if we plug the value, I'll get dt, and we have to do integration to find that, over if I put the value of alpha here, so I get v dv over 100 integration. The limit is from 0 to t for time, and then the for velocity is initial to the final. Now since it's a deceleration, it's opposite of acceleration, so we have to put a negative here. So if we do integration, we get t on the left side, and we get negative, because this is negative. If I take 1 over 100, so that's 0, 1, and then for v, it'll be velocity square over 2. The limit would be, upper limit is 0, lower limit is u. Now t equals to minus negative 0.01 to the 0 square minus u, which is 50 square over 2. If we solve this, then we'll get t equals to 12.5 second. So the time we got positive, and 12.5 looks reasonable, so we got one part of the answer. Required time to reach maximum is 12.5. So we assume the final velocity is 0, because when it reaches the maximum, at that point the final velocity would be 0. So next we need to solve for the maximum height, and how can we connect maximum height with the given function, which is acceleration. So we have the definition of acceleration is dv over dt, but this doesn't have any s, which is distance. So we need to recall another definition of velocity, which is ds over dt. So now if we can simplify and plug the value from this equation of dt here, we can get alpha acceleration a equals to dv, and for dt we get ds over v. So this gives us a ds equals to v dv. Now this is the equation we also derived in our previous theory class, so you can always go back and check. But once we have this, now we can connect our displacement s with a function of acceleration a, and we're ready to do our integration. So um, um, we will get ds equals to v over a dv, and again integration. If we plug the value of a here and simplify, we will get ds integration on the other side, and a, we know acceleration is negative 100 over v dv. The limit of s is 0 because we don't know an initial position. We assume that is 0, so we know the final, we want the final, that is s max. Initial velocity is 0, final velocity, initial velocity is u, I'm sorry, and the final velocity is 0. So if we solve this, we get s on the left hand side, which is the s max. On the right hand side, we get negative 0.01 and v squared dv, u to 0, which gives us negative 0.1 v to the power cube over 3 from 0 to 50. So if we solve here, we get 50 to the power cube. Let me clear this. 0 because velocity is 0, so negative minus 50 cube over 3. If we solve this, we'll get s max as 416.67 meter. So this is our s max. So this is our second answer. So we have answered both of this. We have found t and we have found s max. So this is how we solve this problem. Now let's do some discussion on the problem, so that we can understand the problem better and we can use this understanding to solve other different problems. So we know, we have learned in previous theory class the basic concept: position or displacement, delta s, velocity, acceleration, and time. So these are the four variables we can play with. So now in this problem, the acceleration was given as a function of velocity, right? So what if the acceleration was defined as a function of time or as a function of distance or displacement? What should be our approach to solve the problem? Well, since for this case, for the first scenario, acceleration is given as a function of time, so we can still start with a equals to dv over dt and solve as a dt dv, and we can perform integration on those because a is a function of time, so it will be perfect with this. And then we can go for solution. Now for this one, a is a function of s, displacement. We have to connect acceleration with displacement to solve the problem. We cannot use the definition to start our solution. We can use the equation that we just derived, this equation that connects a with function of s, so we can have function of s ds, which is good for integration, and v dv. So this will be our plan to start solution for if acceleration is defined as a function of distance or displacement s. So this is the solution of the first problem. Let's move to the second problem that we have for today. It says a car is moving along a straight path. So this is the assumption, straight path, meaning rectilinear motion, at a speed of 50 miles per hour. So what are the things given are knowns? Knowns are u equals to 50 miles per hour. Now see, the unit is not a meter in second, so I would like to convert it to meter per second, and the conversion is 0.447, so we got 22.35 meter per second. So this is the unit conversion. It also says that the driver noticed an obstacle it should be 20 meter ahead of the car. So obstacle at 20 meter distance, and the driver applied a brake of acceleration a of 10 meter per second square. So since acceleration is constant 10, the assumption is continuous motion. Therefore, we can use all the four formula that we have derived in our previous class, and we can use this equation and hope it will be much easier and avoid integration and differentiation to solve the problem. So what are the unknowns? The unknowns are how long, meaning time, does it take to stop the car. So time t to stop the car. Determine if the car was able to avoid collision. So the driver applied the brake, but whether the car will stop before hitting the obstacle, which is 20 meter away. So collision or not. And if yes or if not, what would be the minimum deceleration to avoid collision? So how to avoid collision? So this is the second question. This is the third question, is how to avoid collision. Okay, so now we can start solution. So knowns are initial velocity and acceleration, and we know that the car is going to stop, meaning the final velocity is 0. So when we have this formula from this knowns, we can use from the 4 formula. The simple one is final velocity equals to initial velocity minus acceleration into time. So this will give us the time. If we plug the value, 0 equals to 22.35 negative minus 10 into t. So if we solve for time t, we see that it is 2.23 second. So this is the time that is required the car to stop, to come into stop. So this is after he applies the brake, the car will take 2.23 seconds to come to stop. Now we need to see, the second question was whether there will be collision or not. So we need to find how much distance it will travel at that time. So we know ut minus half 8 t square, because it's a deceleration. If we plug the value, initial velocity and time, u multiplied by time 2.23 gives us 49.84 minus the half into deceleration 10 into t squared, time is squared, so 2.23 whole square, that is 4.973. So if we solve this, we get the distance 24.865 meter. So we found that the obstacle was 20 meter away, so s is greater than 20 meter. That tells us collision will occur, collision will happen. So we need to come up with a solution how to avoid the collision. One of the way is that if we could brake at a higher acceleration rate, we could have make the car stop earlier. So that's what we will be looking for. To find that, we'll be using the other second velocity formula, which is v square equals to initial square minus twice as. Because now we selected this equation because we know initial velocity, we know that the maximum s could be 20 meter. We are looking for the minimum acceleration that will stop the car exactly at 20 meter. We can always go higher than this, the minimum acceleration that we'll be finding. It will stop before 20 meter, but we want it to stop at 20 meter, and then the question asking for minimum acceleration required to stop it. So at the stop point, velocity, final velocity is 0. We know the initial velocity is 22.35 whole square minus 2 into 10 into 10. We're looking for the acceleration, so we'll keep that, and then the s displacement is 20. So if we solve, we get acceleration is 12.5 meter per second square. So this is the minimum acceleration mean required to stop the car to avoid the collision. So this was our final unknowns that we found out. So we have answered all of the three, so we solved the problem. Now let's move to the third problem that we have. It's a very simple and small problem. It says a jet plane touched the tarmac at a speed of 150 meter per second. So knowns are u, initial velocity is 150 meter per second. The plane is accelerating at a acceleration equals to 75 minus 0.5 s, that is displacement in meter, and the unit is meter per second square. So what are done? These are the two knowns. It says, okay, what are the unknowns? Okay, before unknowns we have another known that is traveled 409.487 meter. So distance traveled s is 409.807 meter. Unknowns. Unknown is determine the speed. So speed is p, or I can write sp is what? So we need to find the speed. Now solution. So we saw that the acceleration is again a function of displacement s. In the first problem we had the acceleration as a function of velocity. Now it has a function of s, and this is 5. So we know that it's a changing motion. We cannot use the formula, so we have to use an integral form. And to connect acceleration with displacement, we know that we have derived in previous problem a ds equals to v dv, and we can do integration. We can plug the value of a, that is 75 minus 0.5 s ds equals to v dv. If we do the integration, we got 75 s minus okay, the limit is from 0 to 409.807. So why the initial position is 0? Because it starts as soon as plane hit or touch the tarmac. So that's the 0 point origin, and it travels this length, this distance. So this is the final, and the velocity, we have an initial velocity at the touchdown, which is 150, and we want to know what is the final velocity is. So that's we don't know. So if we do the integration, we see 0.5 that remains s square over 2, and limit is from 0 to 409.807. On the right hand side we got v square over 2. The limit is v from 150. Now if we solve, if we take this 2 out and move on the other side, we see we got 150 s minus 0.5 s square on the right hand side, we got v square minus 150 whole square. So if we take everything on the other side and plug value s equals to 409, then we get a equation negative 0.5 s square plus 150s minus 150 whole square equals to v square. So if we solve this, we can get the value of v. So let me find. So if we plug the value in calculator, 0.5 into s is 409.807 whole square plus 150 multiplied by 409.807 minus 150 whole square okay, so this will be plus, because this one, if it goes on the other side, it will be positive. So what we got is I'm working on the calculator. So the velocity is 0.4 meter per second. So it's almost about to stop. So this is the final answer. So today we have solved 3 problems. In next video, we will study curvilinear motion, which is a particle motion moving along a curved path. So far we have studied particle moving in a straight line, and study the theory of particle motion moving in a curved path, and in the next class we'll solve problems. Thank you so much.